We are a multidisciplinary senior design team here at Oregon State. My name is Ashley Greenacre.
And I'm Christopher Harper.
And I'm Stephen Austin.
And we are Team Autosafe.
So we'll start off with a quick overview about what we're going to be talking today. First things first, we'll give some background about our project. Then we'll talk about the challenge definition, what we plan to accomplish, our solution, how we plan to fix that challenge, go into our block diagrams, give a quick demo, and then discuss our engineering requirements.
In the US alone, there are over 10 million motor vehicle accidents each year. If you could know when an accident had occurred on the road ahead of you, wouldn't you want to? We believe that if cars could talk, everyone on the road would be safer. This is why we developed the AutoSafe system. This is a system which combines sensors, networking, and an in-vehicle display that users can plug into their vehicle. These components work together to detect accidents and communicate with other vehicles around them. When an accident is detected, an alert is sent through the network and are displayed on the in-vehicle user interface. Thanks to this system, users may see that an accident has occurred on the road ahead and react accordingly.
Our project aims to meet a few different challenges. The first being visibility challenges. If you're driving through fog and you don't know what's ahead, it will be harder to respond in the case that something goes wrong. Additionally, we want to address compound accidents. If there's a bunch of cars around the corner that have just crashed and you can be informed about it, then you can possibly do something to prevent that. It can help your reaction speed. Additionally, car information accessibility could be better in vehicle, such as certain diagnostic information about your car that could be helpful in determining whether or not you're going to break down, which could be the cause of an accident. Additionally, we found that emergency response time takes an average of 10 minutes, not for the responders to get to the accident, but an average of 10 minutes to make the call for the emergency response teams. So our project aims to meet some of these challenges.
Our solution has 4 distinct subsystems in order to meet the challenges we defined, the first being the sensor board. The sensor board contains all of the sensors needed in order to determine the forces on the vehicle, the location and the speed of the vehicle, and also diagnostic information on the systems contained within the vehicle. On the sensor board, all this information is synthesized and then passed on to our second subsystem, the crash detection algorithms. The crash detection algorithms are running on our Intel Atom-based processing computer. While running, this system receives all of the sensor data and can determine whether or not an impact, spin-out, or flip has occurred. Once it is determined that one of these has happened, the information is then sent to our third subsystem, the network. The network is what links all of our systems together. When information is received from the network, it is also retransmitted so other vehicles that may not have received crash information can then receive it. This information is then displayed on our final subsystem, the in-vehicle interface. If you are the vehicle not in the accident and there is a pertinent accident ahead, a warning is displayed on the in-vehicle interface. Once the accident is no longer relevant to your situation, vehicle diagnostic data is then redisplayed.
So now we're going to discuss our project from the point of view of a block diagram. So we're going to start off with the black box. So this conceals what's inside, and we're just going to look at what's interacting with our project as a whole. So we've got motion coming in along with the GPS signal. We've got car OBD2 information that's coming in and going out as we request and gain gain access to information from the car. We've got the car battery supplying power to the entire project. We use a user select system, which we'll get into more later. And then the user vision is our display that we're using as a heads-up display to feed information to the user.
Our enclosure block, located in the bottom right-hand corner of our block diagram, keeps all of our hardware together and also keeps users from accidentally touching the circuitry located within our system. Our processing computer is the brains of our operation. It runs our crash detection algorithms, getting information from our microcontroller, as well as rendering the user interface. This computer has to be fast in order to process the data quickly enough to be useful across the network. So we've chosen an Intel Atom-based CPU in order for this to occur. The OBD2 hardware block is our interface in between the microcontroller and the vehicle's CAN bus. The CAN bus is the way that the car communicates information in between different sensors on vehicle, but we also need that information on our microcontroller. Our microcontroller uses a UART serial interface in order to communicate most efficiently. However, the car's CAN bus is not inherently compatible. Our OBD2 hardware block bridges this gap so that we can communicate effectively. In order to use this OBD2 hardware block, we also have to write some code on the microcontroller in order to request the information that we need. Our OBD2 code cycles between different commands in order to get different sensor data from the CAN bus.
The 9 degrees of freedom hardware block is one of the key components to our crash detection. The 9 degrees it talks about in its name are the X, Y, and Z axes of force using the accelerometer, X, Y, and Z for a gyroscope to detect spin, and X, Y, and Z for the magnetometer to detect where north is, to work as a compass. We primarily use the accelerometer and the gyroscope in our project. Next, we have the 9 degrees of freedom code. This is what allows us to interface between the microcontroller and the hardware block. This code uses two-wire interface, or I2C, to communicate. Another block here we have is the microcontroller. Now, what we use for a microcontroller is the Teensy 3.0, or rather the Teensy 3.1. This microcontroller had enough in and out pins and enough different ways to communicate with all our peripherals, as well as being very compact and lightweight to really get the job we wanted done. Another block we have is the power supply block. This power supply is coming straight from the car. So we're getting the 12 volts right from the battery, which there's a range of that. It can be up to it's usually around 14 volts actually, but what we use is 12 volts, so we had to use a little bit of hardware to make that happen.
One of the sensors on our sensor board is a GPS. We chose the Adafruit Ultimate GPS as the hardware for our sensor board. Then we had to write the code for it, which is this GPS code block. In the code, we are able to get latitude and longitude after the sensor gets a fix, after it connects to 3 satellites or more. We're also able to get speed and other data from the GPS. Another block is this control hardware block, which is the knob that the user interacts with our system. It is made from an encoder and a switch, so the user can switch tabs by twisting it, and then they can select different options by pressing the button. Then the control code was the code written for the knob, and we're able to detect if it turns and if it's pressed. We also had to debounce the switch and send that data in our sensor packet. Next is the power switch for our system. Because we were working with the computer with the Atom processor outside of its enclosure that was made for it, we had to design our own power switch to turn it on and off that the user can press outside of our enclosure that we made. Next is the display. One of our customer requirements was that we chose a display of a certain resolution. So we picked this display because of its high resolution and its size. It's 7 inches diagonally, which is a good size for drivers so they're not too distracted by what's being displayed.
This is our demonstration for our system. It consists of 3 main parts. The first is our driving simulator here. This driving simulator represents you on the road as part of our system's network. Secondly, we have our in-vehicle display. This represents the display that would be in your vehicle as you're driving. It will show information related to your speed and RPM, which you'll see changing from this simulator, as well as other OBD2 data that you would be collecting from your regular vehicle. Third, we have another interface here, which represents someone else's interface in a car that needs to get information related to anything that happens in your car. Okay, here's our demonstration. So imagine you're driving your simulated vehicle down the road. As you begin to pick up speed, you can see on your in-car vehicle interface that your speed is increasing and your RPM is also increasing. Also, you can see other information related to your vehicle that you would normally be getting if you were not inside of a simulator. As you pick up speed, your likelihood for crash increases, and other people on the network need to know about that. So if all of a sudden we end up crashing into this tree here, you can see on that other vehicle interface that they know that a crash has occurred. So here's what happened in our demonstration. First off, we have a script running in the background of our simulation in order to collect data about the vehicle. These are simulated values that normally would be collected from the sensor board in your vehicle. Things like that would be collected from the 9 degrees of freedom board. This information is then sent to the processing computer and processed as if it were real data from a sensor board. Once it has determined whether or not we've been in a crash, this information is then sent over the network as if it were a regular crash to the other vehicle interface.
So now we're going to go over our customer and engineering requirements for our system. The first one was to send 9 degrees of freedom data to the software layer via TTL serial at least once per second. This was a requirement because we needed to update the accelerometer and gyroscope data fast enough that we're getting accurate sensor data from the car to determine if it was an accident or not. The next test was the data transfer one, and that one was send GPS, 9DOF, and OBD2 data in one packet at least 5 hertz. That way we're sending the information fast enough to other cars and to the system to determine whether it was an accident, and then that would be sent to the cars around it. The enclosure test was that no exposed copper wires and no exposed circuit boards were touchable while the enclosure was closed, so that it contained our entire project and also protected the users from any damage that they could do to themselves or to our project. Another test was sending the GPS data to the software layer via serial at least once per second, and that the system must be able to process the data at least once per second. And that was important for the GPS so that we properly update the location and the timestamp, the day and time in the packet that's being sent, so that we can tell if a car has already seen that message or not. Next test is sending OBD2 data to the software layer via serial at least once per second. And that's where we get the information from the car, like the speed and RPM. So updating it at least once per second, make sure that we're getting correct values there.